Edexcel Core Pure, second order differential equations 2, the non-homogeneous case, particular integrals with trigonometric functions. We've previously seen how important it is in these second order non-homogeneous equations to first consider the homogeneous case in order to find a solution which is called a complementary function. We can then consider the non-homogeneous case in order to find a solution which is called the particular integral, and it's together that these two functions create the general solution. So here the non-homogeneous side is 3 sine 2x, so that's the thing that we often call f of x, and the solution to the homogeneous equation is given by this complementary function. So we've written down the auxiliary equation and solved it for m to create the complementary function. And the complementary function, if we substituted that into the differential equation, it would equate to 0. So now we need to look at the non-homogeneous case, and here we need to try y equals a cos 2x and b sin 2x, and the reason we need both of these is that if we just used sine, when we differentiate sine we get cos, and when we differentiate cos we get minus sine. So if we only use sine, we would be generating cos functions as well, and cos would generate sine in the second derivative. So in order to cover both options, sine and cosine, you always need to include both in your particular integral. So now we can differentiate this to get dy by dx. That's minus 2a sine 2x. Watch out for little chain rules as you're going along. And we need to differentiate it again to get the second derivative. So that's minus 4a cos 2x minus 4b sine 2x. We can then substitute all of y and its derivatives into the left hand side of the differential equation, so that the left hand side becomes, so we need a second derivative minus a first derivative. Good idea to use brackets here to keep things neat and organised. And then minus 2 y's. That's a b sine 2x at the end there. So the main thing to notice here, even though there's only a sine 2x in the non-homogeneous case, you need to consider both the cos 2x and the sine 2x in your particular integral that you are going to try, in the function you're going to try. Make sure you differentiate it once and twice carefully, watch out for chain rules, and then substitute all of them into the left hand side of the differential equation. So we can now, having substituted them, say that the left hand side has to equate to 3 sine 2x. So if we now pick out all the coefficients of cos 2x on both sides, we get minus 6a minus 2b on the left hand side, and there is 0 cos 2x on the right hand side, equation 1. And now I'm going to pick out all the coefficients of sine 2x on both sides, so that's 2a minus 6b, and on the right hand side the coefficient is clearly 3, so that's equation 2. And if we solve these simultaneously, we get a is 3/20 and b is minus 9/20, which means we've successfully found a particular integral, and it has the form y equals 3/20 cos 2x minus 9/20 sine 2x. And together with the complementary function, that will give us a general solution. So here you can see how we've picked out all the coefficients of cos 2x on both sides, and over here we picked out the coefficients of sine 2x on both sides to find a successful particular integral. So having found the complementary function and a successful particular integral, if we add these together we get a complete general solution which still contains two constants a and b. And we can look at the effect of these constants and this general solution in a GeoGebra file. So here we can see some interesting characteristics. So at the moment I've set the coefficients, the a and the b, both equal to a half, and I can control both of those coefficients. And one of the interesting things to notice here is that as x gets bigger and bigger, then the dominant term becomes this half e to the 2x, and you can see the red solution getting closer and closer to this blue exponential, which is a half e to the 2x as x tends to infinity. When x tends to minus infinity, it's this half e to the minus 2x term that becomes dominant, and again you can see when x is negative it's getting closer and closer to the green half e to the minus x function. So as I change a and b, you can see as x gets bigger the function stays close to a e to the 2x, and when x is negative the function stays very close to the b e to the minus 2x. Things get interesting when we let a and b get very small. So if we just let a and b be very small, you might notice that it's starting to see glimpses of something that is oscillating here. And if I let b be 0, just make okay, so when b is 0, when x is large the solution behaves like a e to the 2x again, but when x is negative this term's 0, so when x is negative it behaves like an oscillating wave, as you may have seen in core maths. And if we go the other way we can get the opposite effect. So if I set a to 0 and change b, we can see that when b is negative this b e to the minus x term becomes dominant, as we can see on the graph, and the 0 e to the 2x has no effect when x is positive. It's always going to be 0. So now when I change b, I can change the left hand side, the look on the left hand side of the graph, but on the right hand side we can again see that it's behaving like an oscillating wave. And that's because when x is positive we're starting to look at just the trigonometric part of the solution. So by controlling a and b we can see various characteristics of the general solution. And lastly, if I set both a and b to 0, we can see that both the exponential terms have disappeared and we are left with purely an oscillating wave for our solution. So now we've seen that the general solution could be found by adding the complementary function to the particular integral. If the non-homogeneous side of the equation is linear, we need to try a linear function for the trial function for the particular integral. If the non-homogeneous side is polynomial of order n, we need to try a general polynomial of order n. And in this video we've seen that if the non-homogeneous side contains a cos function and or separately a sine function, you must have a combination of the two in the trial function for your particular integral. In the next video we're going to be looking at particular integrals with the exponential function